right. So check the syllabus. Like I said, I did make some changes in class yesterday because of a conference that I got to go to. So there will be class Monday, and there actually will be lab Monday. Class will be the exam over chapters 6 through 8, and then of course the lab is exercise 6, which I'm working on right now. Is that the one I'm working on right now, or is it already posted? Either way, I'll have it ready for you by Monday. The lab technician, Scott Pierce, Mr. Scott Pierce, will be actually covering the lecture exam. He'll be in the room with you, then he'll be doing the lab. He's very familiar. He actually created a lot of these labs, so he's very familiar with them. What I'm going to do Tuesday again, to remind you, is Tuesday I'm still in the conference, but I am going to have lecture. I'm going to record it, whatever chapter we're on by the time we get to that point, which will be decided at the end of this week. But I'm going to record it on a Friday or sometime over the weekend. Regardless, it'll be posted by Tuesday morning for sure. So while we won't hold class Tuesday morning online, because like I said, I won't be available, you will have the recording to listen to. So you can either, if you're one of those creatures of habit like myself, you can get up at 8 o'clock and listen to the recorded lecture, or you can do it some other time. Unfortunately, again, you won't have the chance to interact with me, but by all means, the next day I'll be in class, and if you have any questions about it. So I'm going to run by myself to make an announcement to everybody to remind them of that again about the lecture, because I know I talked about the Monday, but I don't know if I really said lecture Tuesday. Write myself a note, and that way after class I'll make sure to announce that. All right. Any other questions y'all have for me? Nothing? All right, well, I'm going to go ahead and get started. I do want to step back a little bit and talk about this energy thing. Well, Raymond, a lab practical is basically a series of stations that I'll set around the lab. There's, 24 seats in the lab? Yeah, 24 seats. So you'll have 24 or 25 stations, and you'll rotate through those stations. You'll have a period of time to complete. Most stations will have 2, some stations have 3, but there'll be very short answers. There's not going to be essays. The most you would ever write might be a short sentence. So there might be some metric conversions. There might be using some of the formulas like we did in the first lab to calculate surface area to volume ratio. Make sure you look at those questions at the end of the labs. Those practice questions, oftentimes I'll pull bits and pieces out of those for questions. If you don't mind, I think what I'll do is I'll talk more. Well, actually, I don't see you guys again until next Wednesday. That's right. I do have a lab practical review that I had last semester. I have to take a look at it because some of the labs have been changed. I want to make sure. I don't know if it's even applicable anymore, but yeah, if you go through the labs and you understand what we did in the labs, and there was only a few formulas, and understand the formulas, then you'll be fine as far as the labs go. And understand some of the results. Like if I talk about, what was the reason that the ground up Boolean cube dissolved so much faster than the whole Boolean cube when it was put together, right? So you'd want to very quickly say, well, because the ground up stuff had a higher surface area to volume ratio. You see what I mean? Like short answer kind of stuff, or like, again, metric conversion, convert centimeters to millimeters or whatever the case may be, or answer some questions about density and the density of water and just kind of that basic stuff like that. So if you go through the lab and you I'm not going to make you do procedures. I'm not going to say, okay, go in and do lab 2. It's not going to be that. It's going to be, maybe identifying some of the equipment we used or talking about the results, or just some of the basic calculations and numerical things that I think you should know, okay? So it's over labs 1 through 5. So take a look at those. Oh, the microscope, you'll be looking in the microscope. You'll have to be able to calculate cell sizes. You'll have to answer some questions about the microscope, about the objectives, and good morning, ladies. I'm sorry, I didn't see you came in. You'll have to answer some questions about the objectives, their names, what they're used for. Study that page in the is that lab 4 with the microscope? Study that page where I identify all the microscope parts. And take a look at that picture too, by the way. That is a picture of your microscopes. I took that picture. So it's not like it's going to be in a different spot, which sometimes it is, on a different microscope. No, it's going to be that microscope right there. So study through that, labeling the parts as what, because I may do that, put tags on the parts. What's this part's name? What's it do? things like that. You go around individually, like I was saying, what it's going to be is 24 stations scattered throughout the lab room, and then you'll sit at a station. There'll be a couple of quick questions, and then after a period of time, you'll move to the next. Station. So it's like a musical chairs kind of exam, maybe. I guess it's the best way to think about it. Any other questions? Yeah, we're good. Any other questions for me? Don't get yourself all mentally worked up about the lab practicals. Take them seriously, obviously, but don't, if you've gone through the labs and you knew what happened in the labs and you're able to talk about the results, then I think you'll be fine. All right, if there aren't any other questions, then I'll go ahead and get on into lecture. Like I said, I want to step back a little bit. I gave you the formula up here because if you're one of those mathematical folks or you've had a physics or class like this before, you might remember that what we're calculating, this is delta, that's what that's called. Delta G is the change in free energy. When we're talking about this whole idea of metabolism, we're talking about changes in energy, right? Free energy, again, energy that's, I looked up, I was between free energy, non-free energy. Oh my gosh, it's too confusing. But I always think about free energy as the energy available to do work, all right? So delta G is the change in free energy, and that's what this is all about. So when you eat food, the food loses the energy, right? Because you're eating it, you're digesting it, and you gain the energy. So it's a change in free energy that occurred. Somebody lost and somebody gained. And the reason why I kind of want to go back and review that for a second is, again, if the diving board thing makes sense to you, because what they're talking about in the diving board is gravity. Gravity drives things, obviously, right? You roll a boulder down the hill. But if that doesn't make sense to you, then do what I used to do. Go, what? This made more sense to me. In the world we live in, there is the universe, Mother Nature likes things equal. She likes things, the word is homogeneous, okay? She likes things all being not the same necessarily, but everything spread out. For example, we talked about diffusion, right? You see in the picture, that tendency for molecules or for things that are clumped together at the top to spread out is natural, normal, it's spontaneous. Remember, it's passive. Rocks roll downhill, not because of any magic, because the same reason that dude falls off or jumps off the diving board. Hopefully he didn't fall off. They roll downhill because of gravity. So there's a natural tendency for that to happen. Gravity is a natural thing. Diffusion is a natural thing, okay? Diffusion, molecules want to spread out because Mother Nature likes to spread things out and make them even. As a matter of fact, that's what the universe is doing. If you've ever heard about them saying the universe is expanding, of course, that always blows my mind because I think, what's it expanding into? I blow a balloon up in a room, it's expanding into the room, but apparently cosmologists tell us that it's not that kind of expansion. Anyway, the reason why it's expanding is because it's trying to spread out. It's trying to even out, right? So there's this natural tendency for that to happen. Now, that was a natural tendency, gravity and diffusion, long before there were living things. So living things come on the scene. And remember I said basically we're nothing more than this really incredible chemical dance. We take advantage of what goes on in chemical reactions to suit our needs. Very specifically, in this case, we take advantage of what goes on in chemical reactions, this idea of to releasing energy for our needs. All right, so on the last picture, that at the top could be glucose, let's say. So it's sugar, energy, right? And what we're saying is there's a natural tendency for things, bigger molecules, to fall apart into smaller molecules. There's a natural tendency for that to happen. If you left glucose sitting out for a long time, it would eventually decompose into its byproducts there, right? What living systems do is we kind of tap into that natural tendency. Now, we may make it more efficient, we may speed it up, but what we do is we actually just encourage this natural tendency for things to fall apart. Because if you look back over on the left, when things go from more organized, like glucose or here, to less organized, like in those two, the G changes, right? There's that delta G again. At the top, the G is higher. At the bottom, the G is lower. So G changed, all right? So it was a delta G. And that's the idea. If there's a higher and a lower G, more energy than less energy, Now, remember, the laws of thermodynamics tell you can't destroy energy. So it wasn't destroyed. It was transferred. And this is where living things come in, right? We insert ourselves right in here in this natural tendency, and we take advantage of that fact that energy changes, and we use that energy. We accumulate that energy and use it for our own cellular work. Now, again, the reason why things are falling apart naturally is all about stability. And I've said that a bunch of times, even when we were talking about atoms. Things, diffusion occurs, bigger molecules break down into smaller molecules because of stability. They're less stable when they're concentrated, okay, the top pictures, more stable when they're diffused out or when they're broken down into smaller molecules, okay? Now, one last little thing I want to point out is remind you a relationship between energy and work. Now, it seems obvious, and like I said in class, I think I told you guys yesterday, I'll ask students, so what can you do with energy? And I go, I don't know, kind of an open-ended question. And then I reverse it, and it's pretty simple. What can you do without energy? Right? You can't do anything. So those molecules, like the glucose there on the top, when it's together like that, it has a greater work capacity. Greater work capacity, because in order to do work, you need energy. So there's energy in that molecule. And then when that's released or transferred, not destroyed, released, and we, transferred to us, the molecules at the bottom have less work capacity. It's all kind of related, really. The energy and the work are related. You have more energy in the molecules on the top, less energy in the molecules on the bottom. You have a greater potential to do work with the molecules at the top. You can't do any work with the molecules at the bottom. Now, as I said, we insert ourselves in between. And we use that transfer energy to our own means. Again, these processes are chemical processes that occur whether we were on the planet or not. Not the glucose one. If we were on the planet, there wouldn't be anything to make glucose. But anyway, you get the idea, right? These things are spreading out. So really what we're talking about in Chapter 8, of course, is not creating energy, because you can't do that. Or really what we're talking about, metabolism. We're not destroying energy. We're just basically transferring it. What we're going to really look in Chapter 8 as we kind of move through the rest of the chapter is how can we make that process efficient, right? This process of these molecules falling apart and releasing energy, that's going to happen, right? We have certain reactions that are exergonic that we talked about. The reactants up here at the top, they have more free energy. That's going to be that G again. And you notice when the energy drops, that's a change in energy, okay? So there's a delta G. And when you're looking at an equation that's giving you a number for G or delta G, there's a really good rule of thumb to know whether it's an exergonic or endergonic reaction. I mean, looking at these pictures, it's easy enough, right? The one at the top is exergonic because the products don't have as much energy as the reactants, so the energy had to have gone somewhere. Remember, you can't destroy it, right? And the ones down below for opposite makes very, very good sense too. But you'll notice equation-wise or mathematical-wise, if it's an exergonic reaction, delta G is going to be a minus number. It's going to be less than 0. And if it's an endergonic reaction, delta G is going to be a positive number. It's going to be greater than 0. Okay? So keep that in mind, because when we look at some numbers here, it'll help you understand is it an exergonic or an endergonic reaction. And remember I said in class that these things kind of work together like gears would work. Like, this gear turns this way, which causes, oh man, I'm not an engineer. Yeah, this gear turns this way. And then you can add other gears to it. So what we say is exergonic reactions where energy is released. Let me get rid of my scribbles. So essentially in this picture, this energy here could be used to drive that process there, right? So when you eat food and you release energy, the energy you release could be used in your body to take, oh, I got an example for you. Down below, what you could use that energy for is you could link amino acid number 1 to amino acid number 2, right? That peptide bond. Remember I said covalent bonds represent something physically, a sharing of electrons, but they also represent energy. It took energy to put those two together. So you see, when you eat food, one of the things you could be doing is using that energy to link amino acids together to make proteins, right? To make proteins. And your body has lots of use for all of them different kinds of proteins. Make sense? We're all savvy on that? All right, let's see how much you were paying attention to that delta G thing. Skip this one for a second. I actually removed that slide. It has a point to it, but it just kind of takes you off on a tangent sometimes, I think. So don't worry about that. Okay, so here's ATP. ATP is the shuttle. It's the shuttle between the bagel and the place where proteins are being made, then in the ribosome, right? It's what moves the energy. That's why we call it energy currency. It's what moves the energy, transfers the energy from the food that you eat to whatever cellular process, whatever cellular work you need to do. And remember, you have to do cellular work because you have to remain organized. We talked about that the first time in class, organization, metabolism, how they're related. You got to be organized, and that takes energy. And the way you get that energy to stay organized, or not, get that energy, is you undergo metabolism. And ATP is the shuttle again. So over here is the bagel. There's energy in the bagel, and what the bagel does is it uses its energy to put a molecule together, right? Molecules that are bigger breaking down release energy. When you want to put molecules together, you require energy. So that is a bagel, folks. So you're using the energy in the bagel to stick that phosphate onto something that already has two of them, adenosine diphosphate, like the one down below. Okay, so look at that. That's the energy right there. You don't use, as I said, you don't use bagel energy to do cellular work. You don't use Big Mac energy to do cellular work. You use the energy in that to develop a currency, to increase your ATP in your body. You understand what I mean? I'm sorry if I got a little squirrely there, but ATP is what is the movement between the two. It takes the energy off the food and transfers it to the cell where it needs work. Okay, now up at top, here, at the top, look at that number there. That number, as I mentioned the other day, is the amount of energy. Calories is energy, right? We all know that. It's the amount of energy that's released when those bonds are broken. You see, ATP has 3 phosphate groups, and all those bonds are covalent, yes. But kind of like the peptide bond in proteins, these are special bonds. Special because of the amount of energy that's in them. Now, why is there more energy in those bonds than other covalent bonds? By virtue of the atoms that are stuck together, okay? So when you cleave, all right, when you chop off a phosphate, when you need to climb stairs, build a protein, or when you need to, ouch, just bumped my elbow. When you need to use energy somehow, you chop off one of those bonds. You turn ATP into ADP, and then you release that energy, and that energy does whatever it wants. You know, why right now you're taking notes or you're listening to me, and this is all happening. And then, of course, as I mentioned at the beginning, then you've got to replenish your currency, and you use the energy to put that phosphate back onto the ADP. Now, a little later on, we'll actually find out there are some cases in which it goes even further, and the energy demands actually take off another phosphate and make AMP. So they chop off that second phosphate. Typically, your body cycles between ATP and ADP. When you get down to AMP, that's pretty low. You can't get any more energy out of AMP. You can't chop off that last phosphate. Okay, now up at the top, the minus 7.3 kilocalories per mole. Mole is a measurement of how much there is. The kilocalories we talked about yesterday is how many calories. The minus, so when you break off those phosphate groups, when you cleave those bonds like my little blue line, what does the minus tell you about the type of reaction? Exergonic or endergonic? The minus sign. That's a minus delta G. Take a look at that previous slide a second. All right, go back to here. Oh, not there. See? Yep, it's an exergonic reaction. The delta G is less than 0. It's minus 7.3. Right? So in that particular case, what we're saying is the energy is released. Now, if we had a value plus 7.3, that would be an endergonic reaction. And interestingly enough, think about this. If climbing stairs, taking one step up to the next stair with one leg, takes 7.3 kilocalories in order to be accomplished per mole. Okay? I don't know if that's the right number. It doesn't matter. What we're saying is one ATP molecule chopping off one phosphate, it's just enough energy to lift your leg and put it on the next stairs. Now, I'm really estimating the amount of ATP. It literally takes hundreds of thousands of ATP for that to happen. But you get the idea, right? Each of those ATPs, when they're getting cleaved off, when that last phosphate's being chopped off, 7.3 kilocalories of energy per mole of ATP is being released. Now, if you remember about moles, what you would do with moles is add up all those atoms, all their atomic weights, and what that is in grams is 1 mole. So that's an awful lot of energy that's being released. Okay, and that energy, like I said, with the gears of the clock, the energy that's being released, this exergonic energy that's being released from the ATP is happening over here, right? Energy is being released from ATP. ATP is being turned into ADP because you want the energy to build things up. You want the energy for endergonic reactions, right? So ATP releases the energy. That's an exergonic reaction, and that's used to drive endergonic reactions, climbing stairs, building proteins, etc., 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 right? When you are back here with the bagel and your body is digesting it, and your body's putting the bagel food, the nutrients, into a process called respiration, then you're releasing energy. That's an exergonic reaction. Exergonic reactions drive endergonic reactions. Endergonic reactions can then produce molecules that can turn around and release energy again. It's all those wheels turning together. Okay? So again, don't confuse the terms catabolism and anabolism. The way I always remember, in class I told you that the steroids that some of the athletes were accused of using in baseball, or proven in some cases, I guess, were anabolic steroids. And no professional athlete who's using performance-enhancing drugs would want to take a catabolic steroid, right? That's worse. That tears down molecules. Remember, catabolism, like a cat rips things apart. So always remember, anabolic steroids is to build up. So anabolism is endergonic reaction. It's a building up. It's linking. When you link those amino acids, that's an anabolic reaction. When you digest the bagel, that's a catabolic reaction. We good there? A lot of terms, huh? Make yourself flashcards. That's what helps. Cool. Okay, so what I finished up with, I wanted to show you an example where we're going to go by increasing efficiency. So again, what we're saying up at the top is this glutamic acid and ammonia combining together to make glutamine. Well, while that can happen, there is a cost. Yeah? Look at the sign on that delta G. It's a positive sign, right? So what kind of a reaction is that? So to stick glutamic acid and ammonia together, you're going to need energy, aren't you? Yeah, that's an endergonic reaction. Okay, so that wouldn't happen. You could take a beaker of glutamic acid, a beaker of ammonia, mix them together, and ain't nothing going to happen. Nothing. You're not going to make glutamine because you need energy to do that. It's kind of like going to Home Depot and buying a bunch of lumber and drywall and all kinds of things to make a house, then piling it on the land and go, okay, you're not done yet. You're going to have to make the house, right? So along in the second box, what we're trying to show is if there's something that kind of helps push the reaction along. Now, there's a term for that we're going to introduce. Well, we can introduce it now, as a matter of fact. It's called a catalyst. A catalyst is something that causes something to happen. You hear it all the time, right? The catalyst of the riot was this. The catalyst in this chemical reaction was this. The catalyst that turns your macaroni from hard, really chewy, not chewy, but hard stuff to soft and chewy is heat. Okay, that's why you heat it up on a stove, obviously. Now we're going to talk about a very specialized catalyst later on, or just the next slide actually. But in this case, ATP is a catalyst, so it gets a reaction to happen. So here's what happens. Glutamic acid and ATP react, and ATP is turned into ADP. So there's some energy that's released, but another thing that happened is that third phosphate actually attaches itself to the glutamic acid. And what that does is for one thing, it phosphorylizes it. Phosphorylation is a word we're going to see a lot in the next few chapters. So let's define it now. And it's not difficult, folks. If I stick a phosphate group onto you, if I stick a phosphate group onto something, or something gets a phosphate group attached to it, it's been phosphorylated. All right? So in that second picture, or that second part of that picture, we can say that glutamic acid plus ATP causes the glutamic acid to be phosphorylated. Right? Now, there's energy released. Yes, I get that. But remember what I said about stability. Mother Nature is trying to get things to go to stability. Now, when you phosphorylize things, sometimes, in this case, glutamic acid, you make it more unstable. You see what I'm saying? What's happening in living organisms? We're just trying to encourage a spontaneous process. It's kind of like, I'd like to get this boulder to roll down the hill. I need to push it 10 feet closer to the edge of the hill. You're the catalyst. That boulder would never move on its own. Once you've made that glutamic acid a little unstable, then it more readily reacts with the ammonia to make glutamine. Glutamine, and then they left the E at the bottom for some strange reason, okay? So in this case, glutamic acid and ammonia would never mix unless you added that catalyst. Now, we do a little math down below to try and figure out whether that would indeed work. Would ATP be able to do that? And it's about the energy. In other words, does ATP have enough energy to do it? Okay. Well, we need 3.4 kilocalories. Okay. Every time you chop off a phosphate from an ATP, right, you release 7.3 kilocalories. So if you look at that and you do the math, you say, yeah, because the answer comes up to a negative number. The answer comes up to a negative delta G. If it comes up to a negative delta G, then basically that means that process will occur. ATP has enough. You quite clearly see that it does. If you need 3.4, and ATP every time you chop off a phosphate gives you 7.3, you know, again, be very careful with the pluses and minuses here. While it's necessary to use them in math like you see in the picture there, in this case, they're also referring to energy released and absorbed, right? So the energy, when it's a plus delta G, you need energy, minus delta G, you release it. You look at ATP, and that's got plenty. As a matter of fact, ATP has enough to do it twice, doesn't it? It could actually take 2 glutamic acids, 2 ammonias, and link them together into glutamine, couldn't it? Right? Because in the end, it's left with another 3.9 kilocalories. Still got enough energy to do it again. Okay, see how that works? It's like your bank account, folks. Money going in, money going out works the same way. If you have more money going out than money going in, well, then you're going to be on the negative side. Make sense? So catalyst. I like to use analogy. You guys know I use them all the time. It's the way I remember stuff too. To me, a catalyst, a great analogy is, you remember when you were kids out on the playground and 2 kids would get angry with each other and they would start yelling and blah, 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 blah. And it was obvious, or it looked obvious, that they were probably going to end up in a fight. And so students would gather around in a circle because, being kind, benevolent human beings that we are, the idea was, oh, no, guys, please don't fight. You know, let's talk about this. Let's sit down. Oh, no, don't say that about his mother. Blah, blah, blah. You know, let's work this out. Is that what, let's say they're middle schoolers. Is that what middle schoolers do on a playground when a fight's getting ready to happen? Do they all gather around and try to get these guys to resolve their issues in a less violent way? Gosh, no. At least unless middle school has changed for me. All these vicious monsters are standing, hit him, you see what he called your mom? Oh my God, hit him, right? And so eventually the kids are jawing around. Maybe one of the kids who's involved in the altercation backs up against the crowd, right? But what does somebody in the crowd do? So one kid is kind of backing up against the crowd. Maybe he's not exactly wanting to fight this kid. And yeah, there you go. Now, principal comes, big fight, principal comes, grabs the 2 kids in the fight, shirts all torn to pieces, blood everywhere. Well, maybe not blood, a couple scratches, okay? Drags them off to the principal's office where they're disciplined, suspended, whatever the case may be. What happens to the kid who pushed them? What happens to the kid who pushed that one into the other? Typically, there you go. Nothing, right? Guess what? In my analogy, that kid is a catalyst. The kid who did the pushing, he's a catalyst. He caused something to happen. The fight may not have happened. As I said, one kid was backing out. Maybe he was, deferring. But he caused something to happen. Good angle for world star. Sorry, Tim, what's that? But as I said, the kid doesn't go to the principal's office, so he's unchanged. That's what catalyst, the kind of catalyst we're going to talk about, does. It causes reactions. Oh, I got you. So catalyst that we're going to discuss more specifically, something we call an organic catalyst. There it is. Sorry about that. It just went in and out of session. It's so weird that it does that. All right. So I was saying the kind of catalyst that we're going to focus on in more detail now in the rest of the chapter is something called an organic catalyst. Now, hopefully you remember organic means there's carbon and hydrogen. So that's something to do with living organisms. And again, a catalyst, by this definition, a catalyst is something that causes a change but doesn't get changed itself. The catalyst that we're going to be describing, I mentioned to them a couple times already, called enzymes. Enzymes are proteins. See that big blue thing? That's a protein. Big, massive proteins with all kinds of shapes, all kinds of very specific shapes. Based on all that stuff, hopefully you guys told me on the exam about levels of protein structure. We're going to focus our attention, though, on a particular area and the shape of that particular area. It's called an active site. An enzyme, what an enzyme does is it takes a substrate. Now, a substrate is the same thing as a reactant in those earlier pictures. All right, so an enzyme takes a substrate and it binds to that substrate and it turns that substrate into a product. Okay, so basically what it does, if we use abbreviations, the enzyme plus the substrate is going to make it what you see on the right, an enzyme substrate complex. And then coming out of that, there's still going to be the enzyme. It's a catalyst. It doesn't get changed, but the substrates are going to be turned into products. Okay, so beginning and end. Enzyme does not change. It's a catalyst. Okay, now you can help me with this next part. What is going to decide whether a particular substrate binds to an enzyme's active site? What is the one deciding factor? Yep. Now, listen, enzymes are very specific. You have many different enzymes. Oftentimes, you can recognize the name of an enzyme, and you'll see a lot of these. But, hello, mouse. There we go. Oftentimes, an enzyme will end in ASE. Not A. There we go, ASE. Kind of like many times sugars end in OSE, right? Enzymes very often end in ASE. And many times, the name of the enzyme tells you what its substrate is. That's what I'm trying to get at. Enzymes are specific for their substrate. An enzyme only has one set or just one substrate. By definition, all the other molecules around that enzyme are not substrates. Only something that can bind to the enzyme and get turned into a product is called a substrate. There's a specificity between an enzyme and a substrate. It's like a lock and key. That's why you see that written there. Like the lock that opens the key to, or the key that opens the lock to my truck. How does it know that I have the right truck? It's all about shape, right? It's all about shape. The other keys out there don't have the right shape. My key has the right shape, like if that substrate has the right shape, and of course if that enzyme has the right shape, and if it was formed properly, it will, that substrate should bind into that active site in a lock and key. Now, Mother Nature knows that things aren't perfect. And if you've been around for more than 6 minutes on this planet, you figured out that things aren't perfect. So she always, many times, not always, she'll factor in a little fudge factor into things. Like, for example, this induced fit model. That's what I'm getting ready to talk about. If the shape of the active site or the shape of the substrate is not exactly perfect, and they don't always have to be, they can be off by a little bit, and that's going to vary in the enzyme and the substrate. The induced fit model says that the enzyme will accommodate the substrate anyway. In other words, it's like if the key to my truck had a little ground off part, but it was pretty close still to the shape, right? It would still open my lock. You see what I mean? So Mother Nature realizing that although protein shape is very important, you know, if the shape's off by just a little bit, this is an expensive molecule, folks, a protein. It'd be a shame to say, oh man, it's off by in molecule science, just a nanometer. It's the active site is a nanometer too shallow, so the substrate won't bind. Now, Mother Nature says that's close enough. Now, there's a limit to that, obviously, but I do want you to understand that because I do want you to realize that Mother Nature even plays the things aren't perfect game, right? She understands that molecules, every substrate out there, even if it's made of the same stuff, may not be shaped exactly the same way down to the the nanometer scale. Enzymes are really cool things. This is an enzyme. This enzyme down here, there's its name. It's a big, very complex protein. What's cool about this is
this electron microscope picture of the protein. Each of those little the yellow, the green, the red, and the blue, those are all protein subunits. Oh, so this enzyme has what level of protein structure? What level of protein structure does this enzyme protein have? Is it just one protein, or is it many protein subunits? Look at B. It says many of the protein subunits are clearly visible. You got the little blue ball, or big blue ball, the green, smaller balls, the yellow. Looks like 1, 2, 3, 4 different proteins in there. So what level of protein structure is that? Is that a primary or secondary? What are we looking at there? Tim's tertiary is the folding back of the side groups, but we're still in one protein when we're tertiary. Hemoglobin and collagen. What level of protein structure did they indicate, or what did they demonstrate? If you're looking for alpha helices and beta pleated sheets in there to figure, no, this is a more broader picture. The key is this is many different subunits of proteins, right? So this is the quaternary level, isn't it? Quaternary levels when more than one protein bond together to make maybe what you might call a super protein complex. Some very sophisticated proteins that do very sophisticated things, like this particular enzyme, are going to be quaternary level proteins. All right, look at the name of this enzyme. Remember I said it ends in ASE, and oftentimes it tells you what it does. Now, I'm not expecting you know what pyruvate is, and I'm not expecting you necessarily to know what dehydrin is, but this is an enzyme that dehydrogenates pyruvate. You get it? So what do you think this enzyme does to pyruvate? Don't worry if you don't know what pyruvate is, but based on the word pyruvate dehydrogenase, what do you think this enzyme does? Takes away what? You got it. Takes away, yes. It DHs, yeah, hydrogens, right? So what this enzyme does is responsible for removing hydrogens from pyruvate. More on that later. We'll talk more about that later. Now, not all enzymes are named this conveniently, and not all enzymes end in ASE, but often they do, and many times you can get an idea of their substrate, right? Pyruvate is the substrate for this enzyme, and what it does is it's going to take the hydrogens off of it, okay? So in a very basic sense, this is the way all enzymes work. An enzyme can have many substrates that it's going to bind together. It could have one substrate that's going to split apart, whatever the case may be. Things are going to start off as substrates in one way, and they're going to end up in products as another way. There's that equation I wrote earlier, right? But notice that the enzyme never changes. Enzymes are expensive molecules, right? It's kind of like going out and buying a brand new car, driving it home and say, okay, I'm done, sell that. All I needed was a car to get home with. No. You're not going to do that. You're going to keep that car. You're going to recycle that protein. You're going to keep that protein working substrates into products over and over again. Now, question for you. Will that enzyme be able to do its proper reaction? In other words, will it make sure it always has the right active site shape and all? Will it be able to do its job forever? Will it always remain in the proper shape forever? Why? Why won't it? Why? You know, I just said it's a really expensive molecule. Why do we know? Yeah, you put used up in quotes, right? It gets old, doesn't it? System, it's a system. You're a system. The universe, remember we talked about systems, things that are organized fall apart. You remember entropy? Same thing happens to enzymes. They will eventually, after a while, they get worn out. And the active site will start losing its right shape, and you're not going to get efficient reactions. So in that particular case, what your body would do is it would take that worn out enzyme, chop it back up into amino acids. It's a protein, and recycle those again. So you're constantly replacing enzymes because, like anything in life, enzymes get old and we get old. They don't get gray hair, though. I think I was telling you guys the other day, I was looking in the mirror and I said, well, my hair's not, my dad had gray hair at 21. He said it was my fault. But anyway, I was looking in the mirror and I said, I don't really have that much gray hair. And my wife was in the bedroom. She's sitting behind me on the bed. She says, put your glasses on. I put my glasses on. I was like, oh, yep, a little gray. Everything gets old, right? Enzymes get old. Humans get old. It all happens. Now, let's talk about what enzymes do. Enzymes act like that ATP back in that example we saw a couple slides ago. They make things more efficient. That's what they do. They spur on. That's another kind of term for a catalyst. They spur on something. So take a look at this graph. It does a great job of explaining what I'm trying to get at here. Along the X, or the independent axis, is the progress of the reaction. So we're going from reactants to products. Folks, reactants and substrate, same thing. Same thing, what you start with. The free energy, okay? Now, let's look at the graph that's in the black ink first. What that's telling you is this is the way the reaction is going to go if you do not have an enzyme. Okay, so in other words, we're going to start off here, and then we're going to end up here, all right, which is what we want to do. But if you'll notice that the curve, go above this line, is higher than the one that's in the red. Now, I'll talk about the one in the red in a second. Now, what is that curve? That curve is the E sub A. E sub A stands for energy of activation. Now, E sub A would be the spark, okay? Would be the catalyst, would be the impetus. If, back to my rolling the boulder downhill, E sub A would be you pushing it to the edge. Okay, so what we're saying here in the one in the black, if you want the reactants to be turned into products, you're going to have to put in an amount of energy, right? The best way to make money is spend money, and what they always say, kind of the same thing. You got to put in energy sometimes. You got to prime the pump a little bit to get that energy's released. Now, if it's efficient, if you look down here, the amount of energy that's released is greater than the amount of energy you need. And that works the same thing in money, right? If you invest $1 and get back 10, that's good. But if you do it in reverse, that ain't so good. Now, compare the curves between the one without the enzyme and the one with the reaction that does have an enzyme. Notice that the energy of activation, the one in red, if you have an enzyme, is a lot lower. Okay? Efficiency. What an enzyme will do is it doesn't remove the cell's need for energy. You notice there's a little hill there. E sub A involves energy, right? So it doesn't remove the cells or the enzymes requirement for energy. But what it does is it lets you get the same reaction with less energy. So now, instead of investing 1 and getting back 10, maybe you invest a dime and get back $10. You see what I mean? I hate painting houses. I painted my house twice, and I told my wife, that's it, never doing it again. So think about painting houses as an analogy. Without the enzyme is painting the house with a hand brush, a paintbrush. Not a sprayer, not a roller, the old-fashioned hand brush. E sub A with the enzyme is paying somebody else to paint the house. Now you'll notice that both of those things get done, right? But which one do I, being the one who either uses the paintbrush or pays the people who paint the house, which one involves less energy? Y'all never painted houses? Sure, absolutely. That's why I tried to convince my wife. I said, Millie, it's only natural that I should not pay the house. Or paint the house. It's much more efficient to pay somebody. So yeah, don't pull that science crap on me. All right? So you understand what they're doing here? Enzymes are lowering the E sub A. They're lowering the energy of activation. They're allowing reactions to occur in your body that would normally not occur. There are some chemical reactions in your body that can get spurred on to react if you add heat. Heat is not a great form of energy, but it is a form of energy. But the amount of heat necessary would be well beyond your body's ability to stand it. Right? In other words, the heat, you have to jack your temperature up beyond your normal body temperature to get these reactions to work. But the enzyme comes in, changes that. It says, okay, you don't need quite as much energy. I'm going to make you more efficient. Efficient. It's all about efficiency. Gosh, I was just talking again about that yesterday in Bio 2. Organisms have to be efficient, and enzymes help them do that, right? So now we know the purpose of an enzyme, and we know how it does it. Everything in life, whether it's an enzyme or anything that goes on in your body, any metabolic process has got to be regulated, right? And what I mean by regulated is there's got to be a way to turn it on, turn it off, and then everything in between, the way to speed it up and slow it down, right? All of your chemical reactions in your body are not all going on at the same time, right? They're not all going on at max rate at the same time. Reminds me when I taught my daughter how to drive. My daughter has a horrible lead foot. And when I'm driving with her, I always have to remind her, Stephanie, the gas pedal is a variable object. What do you mean, Dad? I say, if you let your foot off it, we can go slower. You don't have to go full gas pedal every place we need to go. After a number of tickets, I think she learned her lesson, all right? But you got to regulate metabolic activities. You got to regulate enzymes. So that's what we're going to talk about now. We're going to talk about how you regulate enzymes. How do you turn them on? How do you turn them off? How do you speed them up? How do you slow them down? Okay, well, there are three basic ways in which this happens. The first two ways I'm going to talk about are, you see in the picture, are something called competitive inhibition and non-competitive inhibition. Non-competitive inhibition is also sometimes known as allosteric inhibition. This one right here. All right, very simple how it works. See a normal binding, enzyme and substrate matches, blah, 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 everything's good. We get a product out of that, just like we've been talking about. Here's what happens in competitive inhibition. A molecule, not the substrate, gets into the active site. It doesn't have to have the same shape as the active site. It just has to be able to fit in there somewhere. Well, you can see what it's doing, and the reason why it's called competitive inhibition. The inhibition is because if the substrate doesn't bind to the enzyme, you're not going to get anything. And the competition, because basically what happens, it's going to depend on who gets there first. If the substrate binds first, you're going to get product. If the inhibitor binds first, you're going to get nothing. Okay? Now, competitive inhibitors and enzymes don't stay bonded forever. They bond and then they unbond, and they bond and then they unbond. So as soon as that competitive inhibitor unbonds, then boom, Katie barred the door, the competition's open again. Whoever gets to the active site first. Now, how would we regulate that? How can we make that go faster, go slower? Let's think about it. Let's take a cell. And in this cell, and I'm just going to use some really simple numbers to make it easy for me to explain. Let's say there are 10 enzymes. And in this cell, there are 100 substrates for those 10 enzymes. Okay? Now, let's imagine that because of some sort of physiological requirement, at this particular time, we want to slow down or even get to the point where we stop this enzyme. So what we might do is in the cell either pump in, move into the cell, or create inside the cell a competitive inhibitor. And let's say we created 1 million of them. So you got 1 million competitive inhibitors, 100 substrates, 10 enzymes. Now, if you were a betting person, if you were going to do a probability analysis on this, is the probability greater that a substrate will bind to the enzyme or a competitive inhibitor? Yeah. Yeah. All right. Now, what if instead of 1 million competitive inhibitors, now we're like a little bit further down the road. Okay, I need to turn that enzyme back on again. We take out the competitive inhibitors, and maybe now there's only 10 competitive inhibitors. 100 substrates. Now, which way does the probability shift? Yeah. You could also do this by changing the number of enzymes, right? You could add more enzymes and take away enzymes. So those three factors, the enzyme or concentrations, the enzyme, the substrate, and the competitive inhibitor, that's how you control the speed. You up the number of the competitive inhibitors, slow it down, or you could have 1 million competitive inhibitors and 10 million substrate, right? And then maybe 10 million enzymes. So however you monkey with those numbers, that's going to control the speed. Simple enough, right? It's all about numbers. If that makes sense to you, then the next one is no big deal, but it just happens a little bit differently. In non-competitive inhibition, something called a non-competitive inhibitor, okay, binds to a site that's not the active site. That was this one in this picture.
but all that work is going to hurt. Yeah, you take lactase enzymes. That's what you do. Yeah, those Lactaid. Take a look at it next time. That's what it'll tell you, that it contains lactase, and it'll say lactase, which you now know is an enzyme, but it probably says lactase enzymes. Yeah. Yeah, if you're lactose intolerant, you either don't make enough lactase or you don't make any lactase. Something that happens in older folks too. Mammals are one of the only human beings, or one of the only human beings. Humans are one of the only mammals that continue to drink milk into adulthood. Yeah, that's why we believe that there's a prevalence of lactose intolerance when you get older. Among mammals, only young, yeah, that's right. Only young animals, get milk from their mothers. When they get adults, it's no longer. Okay, so the non-competitive inhibitor, that other site that it's binding to, the one that's not the active site, is known as the allosteric site. That's why sometimes non-competitive inhibition is called allosteric inhibition. But the reason why it's called non-competitive is because we're not competing for the active site, right? But what the allosteric inhibitor, this orange thing, does is when it binds to the allosteric site down here in the bottom, it changes the shape of the active site so that the substrate can't bind. Now, of course, like the competitive inhibitor, the non-competitive inhibitor doesn't stay bonded forever. After a while, it unbinds, and guess what happens then? The active site goes back to the proper shape, like that. Right? Now, I know what you're thinking. Well, wait a minute. What if they bind at the same time? They can't. They can't. If the non-competitive inhibitor binds first, the substrate can't bind. If the substrate binds first, it changes the shape of the other binding site, and the non-competitive inhibitor can't bind. So there's no... yeah, kind of. There you go. It makes it what we call a conformation change in the protein. It changes its shape. Now, once again, how would we speed up or slow down this process? Same way we did with competitive. We would monkey with those numbers. We would change the number of competitive inhibitors and or the enzyme and or the substrate. So whoever there's a greater proportion of, that's pretty much where the reaction is going to go. Okay. Now, there are other types of allosteric inhibitors that really that don't inhibit but actually encourage. Let me show you what I mean by that on the next slide. Allosteric activators and inhibitors. All right. If we take a look at the enzyme at the top, the allosteric enzyme. So what we mean by an allosteric enzyme is an enzyme that's regulated through an allosteric, through another site away from the active site. You notice the little green molecule is an activator. And what the activator does is it stabilizes the enzyme. And what we mean by stabilizes the enzyme is it stabilizes its shape. Okay? Proteins have a particular shape, but they're kind of moving and swaying around. And if the active, molecules are always kind of in movement, even when all the atoms are attached. If the active site kind of loses its shape and sometimes the substrate won't bind, the activator moves in and chemically binds between the enzymes and stabilizes them. It keeps those active sites from kind of fluctuating a little bit, right? So you get a much more stabilized active form. Now, the opposite can happen if you want to have a stabilized inactive form. So if you want to totally turn the enzyme off, then you can add an inhibitor that binds not to the active site again. The active site is this little squiggly thing. Notice it's non-functional. But what it does is it stabilizes it in the inactive form. And of course, this arrow indicates that moves back and forth as the body requires. So allosteric inhibitors, there are also allosteric activators. Okay? Cooperativity, that's a very interesting thing about enzymes. Luckily for us, this is how the hemoglobin protein, the enzymes in the hemoglobin protein work. And what this does is the binding of one substrate increases the probability of others binding. In this particular example, imagine that enzyme is the one that's in hemoglobin or is hemoglobin, and the substrate is oxygen. So what that basically says is there's 4 binding places on hemoglobin for oxygen. Once the first oxygen binds, it actually makes it easier for other oxygens to bind. And I'm just sitting here thinking to myself, and I've never had a student ask the question, which is actually good, why would it be in the inactive form to begin with? And I really don't know why. I can't imagine hemoglobin would ever not want to carry. Maybe it's when it's carrying carbon dioxide. I'll have to look into that. Okay, questions on that? All right, where are we? Yeah, 8:58, perfect. Okay, now, as you probably know, life is complicated. And even down at the metabolic level, even at the chemistry level, it's complicated. That while there are some reactions that are simple as enzyme, substrate, substrate product, and we're done, most reactions work kind of like an assembly line. In other words, to make a final end product, it's not one enzyme. You're going to need several. In this case, you can see there are 4 of them. So we have initial substrates, and then we have products, but since we're not quite done, we're not going to call them products. We're going to call it intermediate substrates, right? You got A. It's kind of like I said, an assembly line. When you build a car, first you put the bottom down, then you put the engine in. You know, there's an order to it. Some molecules and some products you're making are pretty complicated, so it takes a little more than just, you know, one shot and you're all finished. Well, this process, this metabolic process by which enzymes catalyze a series of steps, sets up for our other type of inhibition that can work, and it's called feedback inhibition. Now, write this in your notes. Feedback inhibition. This is the key to feedback inhibition. Feedback inhibition is caused by an excess of the final end product. Okay, I'll show you in the next slide what I mean by that. So feedback inhibition is due to an excess of the final end product. Now, this is extremely clever because this is a great way to self-regulate in living organisms. Now, let me show you what I mean. Here's an example. Up at the top, we have a substrate, threonine. And enzyme number 1, look at enzyme number 1 in purple. Look at its name. What do you think it does to threonine? Deaminates it, Tim. Takes an amine group off of it, right? Okay, so, but here's the situation. We go through a series of steps, and the final end product is isoleucine. Now, what's going on here is one amino acid is being turned into another. There are some amino acids that even though we eat them in our food, we can't absorb them. We still need them, but we can't take them up through our food. So what our body does is it converts one amino acid into another, right? How clever. Remember what I said about feedback inhibition. Okay, feedback inhibition is due to an excess of the final end product. So let's set up a situation here. The cell requires 100 isoleucine molecules to make some protein. So the cell puts in an order to threonine deaminase. Hey, I need you to take some threonine and give me 100 isoleucine molecules. Threonine says, okay, sure. Boom, 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 starts cranking it out, cranking out, cranking out. Now, once we reach 100 isoleucine, there are still intermediates in the pipe. There are still intermediates in the works, right? So what we say in chemistry is this reaction is going to have an inertia to it. Now, if I were in class, I could push the chair across the room and let go, and it would still roll. And you all say, oh, yeah, that's inertia. I know what that means. The same thing is happening here with the enzyme. So when we get to 100 and the cell says, oh, thanks, that's the 100 I need, we got all these intermediates, so we actually create a few extras. So I don't know, let's say 50 extra. This is the excess. Now the cell says, okay, I don't need any more isoleucine, I'm done. So that's supposed to say excess, I apologize. That excess isoleucine goes back to threonine deaminase, acts as an allosteric inhibitor, right? Binds to another site, and doesn't allow threonine to bind. Isn't that clever? So what threonine deaminase starts off, the final end product of all of that cycles back and shuts down the very enzyme that created it to begin with. Now this is a perfect way to, if you go on an A&P, you'll learn about feedback loops. This is a perfect feedback loop. It's why it's called feedback inhibition. Now, how do we create more isoleucine in the future? Well, cell uses up that 100. And it says, hey, threonine, you remember that last time you made me some isoleucine? Yeah, make me another 100. Oh, wait, there's 50 right here. I'll take this 50, you make me another 100. Okay, so I take this 50 and I start assembling them into proteins, and guess what? If I take the excess, then there's no excess to bind to the allosteric site. So none of that is going to happen. Okay,
So you mean by feedback, right? This is so cool because when you get into more complex physiology, you realize how well choreographed this chemical dance is that I've been talking about, right? What a great way to limit an enzyme by using its final. You don't need another inhibitor. You don't need to make a competitive inhibitor. You don't need to make a non-competitive inhibitor. Your inhibitor is actually the thing you're making. And when you have too much of it, it makes you stop. I love this stuff. All right. Any questions on that? It's either warming up or my wife turned the heat up a little bit too high when she went to work. But. All right. Next thing I want to talk about, the effects of local conditions on enzyme activity, the effects of the environment. And the first one we're going to talk about is the amount of substrate concentration. So that's the independent axis. The dependent axis is always going to remain the same. The rate of the reaction. Okay. So you notice, and don't worry about what the numbers mean, 0, 5, 10. There's some concentration. So as we add more substrate to a beaker of enzymes, the reaction rate goes up, doesn't it? That makes sense, right? As you add more fuel to the engine of your car, the engine goes faster. As I add more substrate to an enzyme, now enzymes do have an amount of time it takes, mere nanoseconds, if you will. But nonetheless, it does take a little bit of time to take that substrate, bind it, do what you got to do, and turn it into a product, and then release it. So as you add more and more substrate, you'll notice what happens there where I got that sort of blue arrow at about 50, and I just picked that number for no reason. If you notice in this particular case, at about a concentration of 50 moles or whatever that is, the reaction levels off, doesn't it? Saturates. Can your car drive infinitely fast? If my daughter continued to mash onto the gas pedal, would we have eventually reached the speed of light? If you decided to go out for a run this afternoon, can you run infinitely fast? Could you keep running faster and faster and faster and faster? If you've ever been a server at a restaurant, can you effectively serve 8 tables, 12 tables, 15 tables? Now, I've never been a server in a restaurant, but I've heard from some folks that there's, 4 or 5 tables is usually about the most efficient that a server can deal with. I may be wrong on that. But there is something called a saturation point, right? There is a top speed. And that's the same thing in an enzyme. An enzyme turning substrate into product works pretty quickly, folks, but it does eventually reach a point where it saturates. Okay? So that's what increasing substrate concentration will do. Any questions on that? Things can only go so fast. All right, number 2. Same thing on the dependent. All right, but now we got temperature. Ah, man, this is an easy one, especially if you remember that enzymes are proteins. Okay, first of all, explain to me why when the temperature goes up, the reaction rate goes up. Tell me why that is. You guys have forgotten some of the basic stuff I told you back in chapter 2? Or even in diffusion? What happens to, see, if I had the doggone India ink, I could, you guys would probably have a better visual of this. Because the whoing, the whating, the writing. What makes chemical reactions go faster when you heat them up? I mean, what actually is happening to the reactants that make them, the reaction go faster?
Where am I?
Hello? Right, so the molecules speed up. And again, how does an enzyme and a substrate get together? They randomly bump into one another, right? Randomly. So if you speed them up, the chances of them bumping into each other randomly increases. So what happens as you increase temperature, you increase the probability that an enzyme and a substrate will find each other. And the rate goes up, goes up, goes up, and then all of a sudden you're getting really warm, and these molecules are hauling around the place, right? But all of a sudden the reaction drops. Pretty quick, too. Why? Why does the reaction drop when you get, say, this is body temp, 37 degrees Celsius. Why did the reaction in this particular case drop so quickly on the other end? What happened when it got that warm? for that enzyme?
Energy was maxed. Or
Not the energy was maxed. What happened to the enzyme when it got that? What happened to the enzyme, aka protein, when it got that warm? I'm gonna try that one again. Your mic is on, by the way. Your mic is on, by the way. There's only 4 of us. You guys want to leave your mics on? That's fine. Usually, it's a small crowd. It doesn't matter. But okay. Come on.
My God.
So the protein didn't get burned. That's not what happened. But what happened to the protein when for this particular protein when it got that warm? What happens to proteins if they get too warm?
they die, right?
Not die.
Well, melt.
Yeah. That's the word.
Dang! The mic's still on. I'm turning this off because you're recording. Goodbye.
Denature. Yes, Tim, that's exactly what happened. So the reaction is going up. Everything's going great. Oh, wait, let's get warmer, man. We can really get a lot of product. And then, oh, man, you denatured. Denaturing changes the shape of a protein. If you change the shape of a protein, don't you change the shape of the active site? Which means the substrate can't bind. Right? Now, see how this is all tying together, right? What we talked about in terms of a protein and structure and denaturation, that's exactly what you're doing to the enzyme here. You're denaturing. Yeah, same idea. Same idea. Okay, there was one other thing that can denature proteins. Y'all remember what it was? One thing we talked about. We said temperature is one. What was the other one? No. The other environmental condition. pH. Thank you, Tim. There we go. Let's take a look at it. Now along the x-axis, or the independent, we got pH. For this particular enzyme, we are going to have an optimum pH of about, 4.5. That's its optimum when it's got its highest reaction rate. Now, you tell me, why does this happen? Why did this reaction rate drop on either side? Now, notice it doesn't climb slowly like the temperature one. If you think about the question I'm asking, it makes sense why. But what happens on either side of about a pH of 4.5 to this enzyme? It does react more slowly, that's right, but can you tell me why the reaction slows down, Tim? Again, think about what's happening to the enzyme as the pH gets greater or less than 4.5. No. Think about what happens to an enzyme, a protein, as it finds itself in a condition which is too acidic or too basic. Sure. Denatures again, right? Temperature and pH are the two biggest things we talked about that denature an enzyme. So if you take this enzyme in this particular example and you put it in an environment that's beyond 4.5 or less than 4.5, you're going to denature it. So it's a little different than the temperature one that kind of rose slowly because the molecules were moving faster, then dropped. This actually, you get denaturing on either side of the optimum, right? Optimum. Every enzyme, everything's got an optimum, the level at which it works the best. For example, there we go. If we were looking at your typical human enzyme, yeah, but they might be, but since the substrates, since the active site has changed, since the shape of the active site is screwed up, they won't be able to react. They'll just bump into one another. Yeah, that's right. Yeah, that's right. You have the high temperatures, you got them bouncing off each other like crazy, but they just can't fit together. Now, this is one of those no kidding kind of things, but look at the optimal temperature for your typical human enzyme. 37 degrees is our body temp in Celsius, by the way, folks. Makes sense, right? Yeah. Would it make any sense to make the optimal temperature for a human enzyme 45 degrees Celsius? Your body doesn't get that warm. If it does, you got problems. Would it make sense to make the optimal temperature for an enzyme, 10 degrees Celsius? No, because if your body's that cold, you're dead. Now, there are some thermophilic bacteria. Thermo is heat,
And Filicchia knows to love, right? These guys can live in really warm conditions, 77 degrees Celsius. Let me remind you, 100 degrees is boiling. So these, they live in those hot, geysers out in Yellowstone and that sort of stuff. The one you see pictures of them with all the beautiful colors around there, those are all thermophilic bacteria, and they're doing, yeah, and they do well at much warmer temperatures, which again makes sense. Through evolution it does, through efficiency it does. You would definitely want to put enzymes, an organism would definitely want to have enzymes that work optimally at the temperature of that organism usually finds itself. Now for us, we maintain our own body heat. Bacteria don't do that, but that's why they grow in those areas, and they don't grow away from those areas, right? Now the same thing for pH. In your stomach, you have a pH, it's pretty strong acid in your stomach. That's why when maybe you belch a little up, you feel that burn in your esophagus, because the pH of your stomach is down around 2. It's pretty doggone acidic. The optimum pH for an enzyme in your stomach, here's one, pepsin, doesn't end in ASE. It's a protein digesting enzyme. The optimal was 2. As your food moves out of your stomach into your intestines actually become a little more basic. Notice around 8. There's another enzyme in your intestine known as trypsin that continues the digestive process. And again, trypsin has an optimal pH of 8. Now, let's imagine that some of the pepsin in your stomach was to leak into your intestines. And for all I know, it might actually do this. There may not be any problem with it. But what would happen to a pepsin enzyme if it found itself having leaked into the intestines? What would happen to it? What would happen, to it? That's right. We definitely begin to denature. And eventually it would be useless. It's the same thing if you move the enzyme from that bacteria into a human or vice versa. If you move an enzyme away from its optimum temperature or pH, it starts to decrease in its efficiency and its effectiveness. Okay? There's always this really sort of interesting little quip in studying physiology of living organisms. I need to find what it says, but it basically says that physiologists are the only people who get excited about organisms having adaptations that match where they live. It's kind of a nerd humor, but it's kind of like, wow, isn't it kind of cool that birds have wings since they fly? You see what I mean? It's kind of one of those. Yes, it makes perfect sense that the optimum for these enzymes would be, but when we look at it, oh, that's kind of cool. The optimum for this enzyme fits the environment it's found in. Okay, yeah, let me see, we got about 5 minutes. Let me do this slide here. All right, last slide in this chapter. There are 2 things out there. They're called cofactors and coenzymes. You've seen these because they're in your vitamins. You'll see zinc and manganese and all those minerals. That's what cofactors are. Cofactors are non-protein inorganic helpers of enzymes. They help enzymes do their job. So again, they kind of make them more efficient. They tweak them. Coenzymes are non-protein, but these are organic. Things like vitamins are coenzymes. B6, B12. If you do those 5-hour energy shots, they're full of B6, was it B12, or maybe it's both, and they give you a lot of energy. Now, you don't get energy from the vitamin itself. The vitamin just encourages your body to expend energy at a higher rate. That's what that is. So vitamins themselves don't do anything. They just help enzymes do their job more efficiently. I only got 4 minutes, and I got to get into respiration, but I don't. It's a pretty long chapter. I don't want to just give you a couple minutes worth. So I think I'm going to call class early today. So if anybody has any questions, by all means, give them to me. And remember, once again, let me remind you that I am going to record the lecture for but we will have class tomorrow and then Thursday, obviously. But for next Tuesday, I am going to record that lecture and post it. So, all right. That's all I have for you today, folks. So if you don't have anything for me, you all have a nice day. Remember, tomorrow we're doing lab 5. So make sure you download that. Yeah, y'all too. Take care. Oh, I will. Trust me. I don't like cold.
Raymond, you all right? Oh, yeah, you too, Raymond.